Dear students, again welcome back for the sixth session of this solid state. In the previous session, I think I discussed how to calculate the number of particles. I don't know whether the particles may be the form of an atom or a molecule, or sometimes it may be the ions, whatever it may be. So those number of particles that has been present per unit cell of either the three different types of the cubic unit cells. What are that? Simple cubic lattice, and then face-centered cubic lattice, and then the body-centered. So in all the cases we are having the one general formula. What is that? NB plus NF by 2 plus NC by 8. NB is number of body-centered particles. NF refers to which one? The number of face-centered particles, and NC refers to number of which particles? Corner particles. Okay, so usually we have neglected one term that is called as Ne by 8 also, because number of head-centered particles are found to be the Ne is nothing but the number of what particles? Head-centered particles, and its contribution is 1 by 4. But in case of the three unit cells called as SC, BCC and FCC, we didn't have the what particles there? The head-centered particles. Therefore, we are neglecting the term that is Ne by 4. Okay, based on that, with respect to SC, BCC and FCC, the number of lattice points are 8, 9 and then 14. Whereas the number of particles per SC, BCC and FCC are found to be 1, 2 and 4 respectively. Okay. So this is what we have discussed in the last session. Okay. Now we will have the closed packed structure. Closed packed structure with respect to solids. Okay, closed packed structure with respect to which one? The solids. So here, as if according to the standard definition of a solid, solid is one of the physical state of important physical state of matter wherein the particles are close and compact with higher rigidity. So here we are going to study, or when you are going to study the very close packing of arrangement, here the particles are considered to be the lattice points in which the intermolecular force of attraction between them is weak. Strong. Intermolecular force of attraction between them is going to be the strong, and then intermolecular distances are found to be short. That's the main concept. First, as if the particles are very close and compact, means the intermolecular distance between the two adjacent or the neighboring particles is going to be very, very short. But as if they are very close to each other, means we can expect the higher or the more intermolecular force of attraction. So here these lattice points considered to be the hard spheres. The particles indirectly on the form of lattice points, they are considered to be the hard spheres, such that they will touching with each other. Touching with what? Each other. Okay. So let us have, this is one particle, this is one solid particle. So don't mention too far there. Okay. These are the two particles here. So this is the intermolecular distance between the two particles, if that be the case. So here this particle is assumed as the sphere, and this is also assumed to be the sphere like this. Means the individual lattice points are indirectly the particles in the solid. They are considered to be the what spheres first? They are the hard spheres. If they get smooth, they get compressed, which may be either a property with respect to the liquid, or sometimes it may be the extent of the gas. But here, those particles which are considered to be the what spheres? The hard spheres, and they will start to touch with each other, because the intermolecular force of attraction is going to be very, very strong because of the very shortest intermolecular distance. Okay, so that is a main condition where we are going to study when we are studying the close packing arrangement with respect to which one? Solids. Okay, so let us have, this can be studied under three different alignments or directions also we are calling this. Then we will have the dimensions. Let us have the first one. Close packing arrangement in one dimensions. First we will have the what? Close packing arrangement with respect to only one dimension. So here, this is one particle where the position of the particle is found to be at the center. Okay, this is the second particle. Okay, the particle position is exactly at the center. This is the third one at the center. This is the fourth one. At the center we are having the particle. So this is the fifth one. Okay. What at the center I am reading? The position or the rigid point with respect to the particle. It is called as a lattice point. And that particle is now considered to be the what spheres? They are considered to be the hard spheres. This is sphere 1, this is sphere 2 for example. They are almost touching with what? Each other. Okay. So here, this is found to be the linear. This is one particle. This is another particle, this is the third particle, this is the fourth particle, and this is the fifth particle, and it gets extended. Okay. So here, the geometry with respect to this one is found to be the linear shape, or it may be the geometry. Means the close packing arrangement in case of what dimension? One dimension is found to be the what? Linear shape. With the coordination number of 2. With coordination number of what? 2. And this is of the type A type here. Means all the particles are found to be the what? Same in only the one direction. Let us assume this is found to be the x-axis for example. Means it is called as one dimension. In one dimension, how the particles are arranged? Linearly. How it is linearly? One particle adjacent to the another particle adjacent to the another. Means if it is in one direction, means it is having a diagonal shape, or it is also called as the linear shape, such that suppose if I consider this particle, this is shared, not shared, it is surrounded by two neighboring particles. If this is the case, this is one neighboring particle and this is a neighboring particle. Therefore, how many nearest neighbors with respect to that? It is found to be the 2, and that 2 is called as what number? Coordination number. Suppose if I consider this, again it is surrounded by two neighboring particles, hence the coordination number is 2. If I consider this particle, again it is considered by, or it is surrounded by two neighboring particles. Therefore, the close packing with respect to one dimension is having the what shape? Diagonal shape, or it may be sometimes the linear shape, with the coordination number is found to be the what? 2. And this is of the type that is called as AAA type here. Okay. So let's have the geometry with respect to that first. Okay. So assume that this is one particle here. So here, this is 3 dimension that I already mentioned. Now assume that this is one dimension first. This is the position of the particle. This is the lattice point. This is the lattice point. This is, if it is considering only along the x-axis, it is the particle 1, particle 2, particle 3. If I consider only along this axis only. Okay. So here, this is surrounded by 2. Assume that if I fix the ball like this, what happens? This position cannot be visible because as it is exactly at the center. We can't have the visibility of this particle. Only when I open up this, they will get. So here, these particles are now assumed to be what in nature? They are found to be the what? The hard spheres, and they are touching with each other. As if the particles are not touching. But how to show that there is a touching of the particles here? When I put the ball like this and I put the ball like this, now it becomes a what? These two spheres are touching with what? Each other. Touching with each other. Let's have the third one here like this. Means what these are? They are the linear arrangement of which one? The solid state with respect to one dimensional. So here each neighboring particle is surrounded by, or each particle is surrounded by two neighboring particles, hence the coordination number is going to be what? 2. If it is a what dimensional? One dimensional. Okay. Suppose if I make arrangement like this, it becomes, if I arrange like this, one behind the another, it becomes a one dimensional like this. Okay. So here we are having the linear arrangement. This is called as what? Linear arrangement of the which one? Particles. So this is particle 1, particle 2, particle 3, particle 4, it goes on because it is n number of particles we are having. But it is only in one direction. What is that? For example, if I consider that to be the what axis? X-axis. So at the center, I didn't observe here actual right now. At the center of this sphere, we are having the position of the particle. At the center of this, there is a position of the second particle, third particle, fourth particle. So here, these particles are considered to be the hard spheres which are touching with each other, as if they are touching with each other. If this be the case, it is a one dimension. Means the close packing with respect to what dimension? It is one dimension, and that is found to have the shape of a linear, which is also called as straight, or sometimes it may be the diagonal. So here, what is the coordination number? Each particle is surrounded by 2, each particle is surrounded by 2, each particle is surrounded by 2. Therefore, the coordination number is going to be what? 2. And then this all particles will have the same nature. Therefore, it is called as A type here. Okay. So that is with respect to which one? The close packing in what dimension here? One dimension. Okay. So let us have the second one. Close packing for two dimensional. Close packing in two dimensions. Close packing in how many dimensions? Two dimensions. Let's have the other one in the form of now we will have the same close packing, but it is in what? Two dimension. Two dimension means one is x-axis, another is a y-axis. So here, the AAA arrangement of in one dimensional, if arranged, it has two different two-dimensional geometries. What geometry we are having? The two different geometries. The first one is square close packing in two-dimensional, and then the second one is square close packing. The second one is hexagonal close packing. Hexagonal what packing? Close packing in same what dimensional? Two dimensional. So don't want to mention the particle size here because okay. So what it is now? The AA type arrangement in what dimension? First only the one dimension. Suppose if one overlaps with another, because as if it is not only along the one direction, it is on the second direction. Suppose if it is X, then we have to have the Y. There are two different possibilities right now. The first possibility is this is one possibility, and so on. Suppose if this is X-axis then this must be y-axis. Y-axis. Means it is a what dimension here? It is a 2 dimension. So if this be the case, this is x-axis, one direction, this is y-axis. If one sphere is exactly below to that in the second layer, if the second particle is exactly below to that in the third layer, again this is of the type called as A type with respect to what dimensional? 2 dimensional. And the geometry for this one is found to be the square close packing. What is the shape of that? It is the square close packing structure, having the coordination number of 4 here. Coordination number of what? 4 here. So what is that here? This is equal towards the length and then the breadth. First it is found to be the square close packing with respect to what direction? X-axis and y-axis means it is called as what dimension? 2 dimension. Okay. So why it is called as square close packing? If I particularly select this one, okay, the nearest neighbors are this, sorry, not this actually. It is not a nearest particle here. This is the particle nearest, this is the particle which is nearest, this is the particle that is very nearest. Hence the geometry for that one is found to be the. So here it is surrounded by what? How much? If I consider any particle, it is surrounded by which one? 4 nearest neighbors, hence the coordination number is found to be what? 4. And the geometry of that particular is found to be the what packing? Square close packing. Okay. So let us have. So I think this is first the one dimensional arrangement of linear structure with respect to the solids. Okay. If I arrange another one, this is another one. Okay. To make a differentiation, let's have the clarity between them in the form of which one? The 2 dimensional as like this. Okay. So this is another, the second layer. If I put one above the another like this, can I say that the first layer is very quite similar to that of the second here? Therefore again it is of the type what is that? A. This is the alignment along the x-axis and this is the alignment along the y-axis. In both axes the arrangement is going to be same. That is why it is called as A. Suppose if I make a clear picture related to that, it becomes like this. This is first one dimensional. If I put another one, what this is? This is called as the square close packing with respect to what dimension here? It is the 2 dimension. Can I say that the first layer is quite similar to that of the second and the second is quite similar to that of the third? Therefore, in both the x-axis and then the y-axis, the alignment of the geometry is found to be same. Therefore, if this is A, this is also A, this is also A, this is also A, that is why it is called as what type? A type. Okay. Now, how many nearest neighbors are there with respect to each other here? Suppose if I concentrate any one of this, suppose if I consider this, I think this is nearest 1, this is nearest 2, this is nearest 3, this is nearest 4. But this is not nearest because there is some gap here. This is not, there is gap here, there is gap here, there is gap here. Means, if this is the center particle that I consider, the nearest neighbors are 1, 2, 3 and 4. And the geometry of that one is found to be the what? Square close packing with respect to what dimensional? 2 dimensional, and the arrangement is similar to that of A type. What's the meaning of A type here? The first layer, second layer, third layer, fourth layer, whatever it may be, in both the x-axis and then the y-axis, it is found to be identical. That is why it is called as A type, which is having a geometry of square close packing. In what dimension? 2 dimension. Let's have the alternate different. What's the different here? The second case is hexagonal close packing in 2 dimensional. Instead of writing the sphere exactly below to that, if I put that in between the 2 spheres of the first layer, I will get the different geometry like this. Okay, now it is a different here. So these are the particles, same positions of the particles. Okay, so here this is of the type AB type we are calling. This is the first layer, this is the second layer, this is the third layer, this is the fourth layer, this is the fifth layer, and then the sixth layer, and so on. Can I say that first and third are same and second and fourth are same here? Means if the first layer is A, then the second layer must be what? B. Again, we are having the C, not the C here, the third layer is similar to that of which one? A. And the fourth layer is very similar to that of the second. That is why it is called as AB type. Okay. If this be the case, the geometry of that particular complex, or it may be the two-dimensional geometry with respect to hexagonal is okay. If I consider or choose the point at the center, how many nearest neighbors are there? 1, 2, 3, 4, 5 and 6. That is why it is called as what? Hexagonal close packing. Which one? Hexagonal close packing. In what dimensional? Two-dimensional. So here the coordination number is going to be what? It is going to be the 6. If I consider the particle at the center with respect to this hexagon, the number of nearest neighbors are 1, 2, 3, 4, 5 and 6. Okay. So let's have the observation for this particular two-dimensional. Let's have the one dimension here. So what this is? It is a linear of one dimension. What is this? This is the two dimension. Such that all the layers are found to be same. That is why this is called as AA type. It is of square close packing. Suppose here the sphere in the first layer is exactly below that of the second and below to that of the third and so on. Therefore, it is called as AA type, which is called as square close packing. But if this be the case, so assume that this is the same as usual. The first layer is same. What is that? AA type. But here in the second layer, the particle is situated in between the two. It is not exactly one below the another. It is in between the two. Therefore, the first layer, can I say that is very similar to that of the second, and the first layer is very similar to that of the third, and then the second layer is very similar to that of which one? The fourth. Therefore, it is called as AB type, and that refers to a geometry called as which one? Hexagonal close packing. Hexagonal close packing with respect to what dimensional? Two dimensional. So here, if I consider one particle, for example, if I consider which one? One particle at the center, like this. How many nearest neighbors are there? 1, 2, 3, 4, 5 and 6. Suppose if I remove this and I will show the exactness related to that, can I say that it is very similar to that? Therefore, it is same. Means it is at the center particle, and this is surrounded by how much? 6. And the geometry with respect to this one is going to be the what packing? Hexagonal close packing with respect to what dimension here? It is going to be the hexagonal close packing with respect to two dimensional with the coordination number of how much? 6. Because at the center we are having the pink color and we are having the 6 neighboring which are found to be the yellow spheres, and the number of nearest neighbors is going to be the what? 6. That is why it is called as the hexagonal close packing with respect to what dimension here? The two dimension, and the coordination number is going to be what? 6. Okay. It is not of AA type. It is called as AB type. Okay, so that is the close packing with respect to what dimension? It is the two dimension. Okay, so now lastly we will move on to the third one, that is called as the close packing in with respect to three dimensions. So I think this is the close packing in one dimension, close packing in two dimensions. Next we'll move on to the third one, that is called as close packing in three dimensions. Let's have the third one now, that is called close packing in three dimensions. Close packing in what dimensions here? Three dimensions. So here we are having the three types. The first one is simple cubic structure in three dimension, and then we are having the hexagonal close packing in three dimension. And last one, we are having the cubic close packing in, again what dimension? The three dimension. Means for one dimension we are having only one, what is that called as a linear, which is of the type A, and the coordination number is found to be the 2. If that A type of the one dimension, if it is arranged in two dimensions, we are having the two different varieties, either in the form of A called as square close packing arrangement with the coordination number of how much? 4. The second possibility is AB type, means the first and the third layer are similar, the second and the fourth layer are found to be the similar, therefore it is called as AB type, and the name of that one is called as hexagonal close packing with the coordination number of what? 6. Now, if the AAA type of the square close packing of the two dimension, if it is arranged in three dimension, means first we have aligned only along the x axis, then we have arranged in the y axis, and then we have to move into the z axis, means we are having the three dimension. The first possibility that I am expecting is going to be the what? Simple cubic lattice. What is that? Simple cubic crystallar structure with respect to what I mentioned? Three dimension. If it is adjacent to that, then it is found to be the hexagonal close packing in three dimension, and if it is found to be the another possibility of the AB type, it becomes the cubic close packing with respect to three dimension. So here what is this first? A linear, that is called as one dimension first. So here, what is this? It is a square close packing with respect to two dimensional. If this is now applied on the third direction, for example Z, how it look like? This is the second layer with respect to three dimension now. Three dimension. This is the fourth layer with respect to dimension, and then like this. So let's have the clarity. So here the geometry of that one is found to be the simple cubic geometry. Simple cubic geometry, or it may be the shape. This also of the type AA type. With the coordination number is equal to what? 6 here. With the coordination number of what? 6. Let's have the first. What is this? It is the one dimensional. Okay, it is called as linear. So if I arrange the same one below the another, it is of the type AA type with respect to what dimension? 2 dimension. Okay. Now, What is this here? This also I think it is AAA type. This also called as AAA type. Both are square close packing with respect to what dimension? 2 dimensional. Suppose if I align them in the, because first I arranged in the x axis, secondly I arranged in the y axis. Now the third one is along the z axis, like this. Or I can take another one also, no problem for that. We'll have this one first. Okay. So what this is? A 3-dimensional close packing of a simple cubic with respect to what lattice here. First this is this one. And behind that what we are observing, we have to make like this. And the third one we have to make like this. And we have to take a photograph from this angle, not at this one. Okay. If that be the case, we are observing this condition. Can you say that the first layer, second layer and then the third layer unfold will be almost the same? Not almost, it is always the same. That is why first it is called as A type system. And what is the coordination number here? And what is the geometry of that? Suppose if I remove this part, particularly part, I will get this one. What this is now? A simple cubic. How many corners we are having? The 8 corners. It is similar to that of this one. This is called a simple cube where we are having the 8 corners, and instead of that I have mentioned that in the form of spheres. Okay. So this is of the type that is called as the close packing in 3 dimensions. The first ever arrangement that I am getting is found to be the simple cubic structure with respect to 3 dimension, and it is of the type same A type with the coordination number of what? It is the 2. So here is as if I just not observing clearly the coordination number here. So if that be the case, this is the quite arrangement with respect to 3 dimension here. So this is one of the part of this. Okay. If I consider the point at the center, 1, 2, 3, 4, 5 and then 6. Therefore, how many nearest neighbors with respect to this? It is found to be the 6. Hence, the coordination number for simple cubic structure in 3-dimensional type, which is of the AA type, is found to be how much? It is the 6. Suppose, if one gets overlapped with the another like this, it's of the type what is that? AA type. This is also of the type what is that? AA type. Instead of putting one above the another, if I put that between the two like this, between the two like this, I will get the final structure in the form of like this. So this is what the geometry that I am observing. When the what dimension? 2-dimensional AA type of square close packing in alternate ways. Means instead of placing the spheres one above the another or one below the another, in between the two, the second layer if it is placed, this is the geometry what we are observing. And this is called as the hexagonal close packing with respect to what dimensional? 3-dimensional. So here this is called, or this is having the of the type, can I say that the first and second layers are different? First and second are different. First and third are same here. Therefore, the first and third are found to be the same. So second and the fourth are also found to be the same. So and this is called as what? The hexagonal close packing with respect to what dimensional? 3-dimensional, which is of the type AB type here. It is called as AB type here. With a coordination number of exactly equal to how much here? It is the 12. Exactly equal to what? 12. Why it is 12 means here, at the center we are having the particle like this. If I choose one particle, single particle at the center like this, and if I put like this, so here this has the 6 lattice points. This has the 6 lattice points, and this exactly at the center, and this also has the 6. Therefore, totally 6 plus 6, that is totally 12 nearest neighbors in case of the hexagonal nose packing of AB type, which is having the coordination number of how much? 12. So here first it is an example for it is a 6 axis fold symmetry. Means we are getting 6 similar structures at regularly by rotating at 60 degree now. So let us have the clear assumption for that. So what is this? AB type. So right now I am taking only this one. Okay. So this is at 0 degree. Assume that the whole of this particular circle is going to be the 360. So these two are below, these two are above, and exactly behind that we are having one particle. Behind that we are having one particle like this. So what is this called as first? AB type. Okay. So this is at 0 degree, for example. So to get the same structure, what I have to do here? I have to rotate like this. This rotation is just only 60 degree. Again 2 plus 2 at the center we are having the 1. If I rotate like this, I am getting the same. That is 2 plus 2 plus 1. 2 plus 2 plus 1. So this is the third. This is the fourth. This is the fifth. And this is the sixth. Means this is called a 6 axis fold of symmetry. It's called as what? 6 axis fold of symmetry. Means I am getting the similar structure by just rotating 2. An extent of how much degree here? 60 degree. Means for every 60 degree I am getting the similar structure. Therefore totally the 360 means we are having the 6 fold symmetry, and it is having a packing efficiency of hexagonal nose packing in this one is going to be the how much? 74%. What is packing efficiency? That I will discuss in the next class. Okay. So here the packing efficiency with respect to that one is going to be the 74%. Here first layer and third layer are going to be similar. Second layer and then the fourth layer are going to be the similar here. Therefore it is of the type, what is that called as AB type here. Okay. Now if the AB type of 2-dimensional, what is AB type of 2-dimensional hexagonal called as? It is the hexagonal nose packing with the coordination number of 12 here. Okay. So here this refers to the cubic close packing. What's that packing called as? The cubic close packing, CCP, which is of the type ABC type. And here it is a 3-axis fold of symmetry. 3-axis what? Fold of symmetry. And then we are having the 3 similar structures regularly by rotating at around 120 degree, and then the same packing efficiency is going to be the 74. Here the first and then the fourth layer are similar. Second and then the fifth layer are similar. Third layer and then the sixth layer are going to be the similar here. So let us have the dimension. So what is this first? It's a AB type or ABA type here. It is called as AB type with respect to 2-dimensional, which is also called as hexagonal nose packing. What is this also again? The same hexagonal nose packing. If I arrange one below the another, not exactly one pointing below to that, between the two vacant spaces, or between the two spaces if I fix the another one. So I will get the total arrangement in the form of like this. What is that? This of hexagonal, this of hexagonal, this of also hexagonal. If I arrange like this, and this is now considered to be the, or I can take a simple this itself. It's not possible here. So first observe the layers first. Here the arrangement is found to be first 2, 2, 1, but the thing is 2 is very far from this, and behind this we are having the another 2, but here it is only 1. Therefore it is called ABC. Next we come with another one that is called as A. Can you say that the first and then the fourth layer are found to be quite similar here? It is found to be the first layer and fourth layer are found to be the quite similar. Similarly, we can have the second with respect to the fifth. I have not mentioned here. And then the third one with respect to this one. Therefore, this is called as cubic close packing. What's that arrangement here? It is called as cubic close packing of the type. What is that called as? ABC, ABC and then ABC. What is that? ABC, ABC and then the ABC. This is called as ABC, ABC, ABC structure here. So this symmetry is obtained by rotating for every 120. In the previous case HCP we have rotated for every 60 degree, we are getting the similarity in the structure. But the similarity in the structure with respect to CCP is at 120 degree, means 120, 120, 120. If I rotate, so it is not exactly here, I have not pinned that. So this is one layer, first, sorry, it is one particular combination, that is ABC. Similarly, we will have the what? ABC. So if the same symmetry is obtained by rotating at 120, similarly at 120. Okay. So that is why it is first, it is called as what? 3-axis fold of symmetry. That is why we are getting the 3 similar structures regularly that has been rotating by how much degree? 120 degree, and the packing efficiency is again found to be the 74, and then the coordination number is also found to be the what? 12. Here also the coordination number. Here also the coordination number is found to be the what? 12. Why? Because as it is a very close packing with the hexagonal structure, arrangement means it is the 12 is the which one? The coordination number. Here in case of HCP for the 3 dimensions, the similarity is between the first and then the third, second and then the fourth. Whereas the similarity is from first and fourth layer, second and then the fifth layer, followed by the third and then the sixth layer. That is why it is called as ABC, ABC, ABC type, and that particular arrangement is called as cubic close packing arrangement. Cubic close packing. So this is called as what? The structure close packing arrangement with respect to which one? The 1-dimensional, 2-dimensional and then the 3-dimensional. So just I will briefly mention that one as close packing in 1-dimensional. It is called as a linear, which is of the type AAA type with a coordination number of 12. Sorry, coordination number of only the 2. Okay. The close packing in 2 dimensionals. We are having the 2. What is that? First one is square close packing. Square close packing, which is of the type same AAA type with a coordination number of 4. The second one is hexagonal close packing. Hexagonal what packing? Close packing, which is of the type AB, AB, AB type. Here the coordination number is going to be what? 6. Whereas with respect to 3-dimensional, we are having the 2 different possibilities. What is that first one? One is simple cubic. Simple cubic, which is of the type same AA type, and the coordination number is going to be what? 6. The second one is HCP. What is HCP? Hexagonal close packing of the type hexagonal close packing of the type AB, AB type with the coordination number of 12. And the last one is CCP. What is CCP here? Cubic close packing, and this is of the type, what is that? ABC, ABC, ABC type. Again, it is having the coordination number of how much it is that. So this is called as the total close packing arrangement with respect to one dimensional, two dimensional, and then the three dimensional arrangement of particles with respect to which one? Solids. Okay. Now, as if we are considered that to be a spheres. When I touch the two different spheres, there are some vacant space inside that. Not inside, it is outside that, in between them. And that particular vacant space we are calling that as the voids. It's called as what? Voids. And what the volume that has been occupied by the hard spheres is considered to be the packing efficiency. Okay, so that we will discuss, but it's both the void concept and then the packing efficiency concept with respect to all the various types of the one dimensional, two dimensional, and then the three dimensional arrangement of particles with respect to structure. Okay, so that all we will discuss in the next session of this particular solid state. Okay, so thank you.